All right, last time we were here, we started this section about multiplication and division with rational numbers, and we had gotten to the point where we were looking at some exponent properties, and I was showing you why some of the exponent properties are the way they are, and we're on number 3. All right, so on this particular property, you have the property already written down. What does a to the m to the n simplify to be equal to? What's another way to write that? Right, Hannah, yes, a to the m times n, so we can multiply the exponents. And I want to show you again why that is. So the part that's in parentheses, a cubed, is the same as a times a times a, right? Everybody good with that? And that is squared, and squared means multiplied by itself. So that's equivalent to having 3 a's and then another 3 a's. So how many a's is that? 6. And how do you get from 2 and 3 to 6? You multiply. So that's why that property is the way that that is. All right, the next one, ab to the m. What was that property going to equal? Right, and many of you sort of had this description of it sort of looks like it's a distributive sort of property. Of course, it's not distributive because that's involving an addition property, but it has this sort of feel that somehow we move one piece and it applies to both pieces inside. So ab to the 4th means that I have ab times ab times ab times ab. I think that's 4 of them. And we're allowed to move values around. Do you remember what the property is that allows us to switch the order of a and b when we're multiplying? Say it, Beth. It's commutative. Very good. That's the commutative property. So if we use the commutative property a whole bunch of times, I can collect all my a's at the beginning, and then I can collect all the b's at the end. And if I do that, you can quickly count, of course, that there are 4 a's, so that's a to the 4th, and there are 4 b's, so that's b to the 4th. You can also very quickly see that if there were addition, we wouldn't have this property. This wouldn't look like this. I wouldn't be able to move things around in this way. So this really is specific to multiplication and division, actually, which is the next one. So what happens on the a over b to the m? Good, a to the m over b to the m. And the way that ends up looking on this, too, is that if I had a over b and I had it 4 times, as we were looking at earlier in this, even in this particular section, we can multiply straight across the top. So that's 4 a's, this is a to the 4th. And straight across the bottom, 4 b's, so this is b to the 4th. What does number 6 do? Okay, so it flips them, right? You switch the location for the numerator and denominator. And then the exponent distributes much like part 5 did, right? All right, so I'm going to treat this very much in that way. So this is a over b. I'm going to talk about the -1 exponent, and then we're going to break it apart to be the power of 4 exponent, because that's the same thing as -4th, right? A power to a power, that's property number 3 that we already did on the previous slide. Well, a negative exponent means to take a reciprocal. That's what that means for us. So this is actually b over a raised to the 4th power. So this negative flips it. And the fact that it's to the 4th power means I can use property number 5 then, right? I could write it out if you want. We could write b over a 4 times. And I would end up with b to the 4th over a to the 4th. All good? Okay, again, let me say this because I said it last time. I have no desire when you're working with these problems for you to write things out longhand. That's not the point of me showing you these 2 slides. The point of me showing you these 2 slides is hopefully you get the sense that it wasn't just somebody that made up these properties, right? They actually are properties because they work. And I gave you concrete examples on each one of them showing how they work. That's all that is really for, is for you to recognize that that's the properties and how they work. All right, 7 and 8. On number 7, we talked about, I'm sorry, we didn't do this one, did we? This one's new. On number 7, do you guys remember what a to the 0 is? 1. Sorry, I was getting confused. I have just worked on some properties of exponents in Math 1. So a to the 0 is actually equal to 1, and I want to show you why, and this is probably the most interesting one as far as I'm concerned. So I'm going to show you why a to the 0 is 1 by rewriting 0 as a number minus itself. So I'm going to write this as, we'll do 5 just for fun. Okay, so do you agree that a to the 0 is the same as a to the 5 minus 5? Okay. I'm going to use property number 2 in reverse. Property number 2 actually has it written like this. And according to property number 2, I could start here where this says a to the 5th of the a to the 5th, and I could write it as a to the 5 minus 5. So I'm just using the property backwards. And here's why. What happens when you divide a to the 5th by a to the 5th? You get 1. And there was really nothing special about the fact that I used the 5 either then, right? I just picked 5. This is actually why the power of 0, a to the 0 power, is equal to 1. Now the other one here, this one is just sort of a version, if you will, number 8 of number 6, where we have the negative exponent. Except that I don't have a fraction that this is applying to. I just have a single letter a. So we have the same idea. Do you know what the reciprocal of a is? Right, 1 over a. So this is equivalent to having 1 over a, and then that a is raised to the m power. So I'm going to do this with the a to the negative 3. So I'm going to write it as a over 1 to the negative 3. I can actually switch it to being 1 over a to the 3rd. And then I can apply that power 3, 1 to the 3rd, a to the 3rd. But what is 1 to the 3rd? It's just 1. So I end up with 1 over a cubed. Just like the original one said, I should end up with 1 over a to the m. Is that good? Okay. All right, so let's do some examples that you'll actually see of how you're going to use these properties now that we've established them. All right, so we have a couple of examples. Part A actually looks most like what I was just using because it's got A's and B's in it. Part B actually has some numbers in it, so it's going to require us to do a little bit different figuring of things out. All right, so on Part A, there's lots of things we could do here. So somebody give me a suggestion. What could we do first, or what is your first step as you look at this to simplifying? Say it again. Move the a to the negative 3 to the top. Is that what you said? Okay. And so we're allowed to do that kind of based on that last one I just did, that number 8, right? This says I can use the reciprocal. Yes, Shayna?
Can't you just, like, take away 2 of the b's, like, on top?
Yes, you can. So let me do those two features. I'll do them one at a time so everybody's clear that they don't really affect each other. So Kenzie wants me to write the a that's there, write another a cubed on top, and then we're going to leave the b to the 4th where it is and the b squared where it is. Okay? All right, so Shayna mentioned, look, I've got b to the 4th on top and I've got a b squared on bottom, right? So if I want to deal with it like that, I could actually reduce this b squared by removing 2 of these b's because there are 4 of them there right now. And that would be okay. Is there any way to combine those a's? It would be a to the 4th because this is understood to be a power of 1 on that a, right? So this is a to the 4th times b squared. Let me show you another version. There's lots of versions, but let me show you another version that you might like too. Another way to think about this is to think about this in terms of subtraction. That is, I've got power of a on top and bottom. So I could take the power of a on top, which is 1, and subtract the power of a on bottom, which is minus negative 3. Right, this is the second property with subtraction. I could do the same thing with the b. The power on top is 4 minus the power on bottom, which is 2. So what is the power of a is going to be 1 minus negative 3. What's 1 minus negative 3? 4. And then what is 4 minus 2 for the power for b? 2. So am I going to get the same answer? Yeah. And there's other options besides this one too. So there's lots of things you could do and all still arrive at the same answer. Part B is a little bit different. It doesn't have any letters as bases. What else is different about it? Okay, so what do you mean by they're separate, Abby?
Like on the top it was AB. When couldn't you kind of divide that into two?
Yeah, you could have sort of separated the A's from the B's, kind of how we were thinking about it. That's true. There's something else going on with this one, though. Okay, they're being multiplied, and we've got, Lydia's saying, we've got different denominators and the different numerators too, right? Like, the things that are inside the parentheses, they're not exactly alike, are they? And all of my properties that allowed me to combine things only allowed me to combine things that had the same base. And these two bases, that is 2 over 5 and 4 over 25, are not identical to one another, right? So I can't just like add exponents or something, because that only works if the bases are the same. So there's got to be something else I can do in order to be able to use these properties. In other words, what I want to do is I want to make the bases the same. Is there any way to change what I have so that the bases are the same? Well, if we multiply by 5, it would actually change the value of the whole expression. We don't have an equation like two sides with equals. But you're on the right track, Lydia, just not quite there. Okay, same thing. If we divide, we're going to change the value. What if we do this? I'm not going to change the first one at all. But I'm going to change the second one to look like this. Okay. This piece right here in the middle is taking the place of where the 4 over 25 is. Because how is 4 related to 2? Well, one way it's related to 2 is because it's 2 squared. How's 25 related to 5? Well, one way it's related to it is because it's 5 squared. So in other words, I could factor it. Another way you could think about it, if you don't like sort of how I did the squares, is you could write it like this. Do you like that any better? It's the same thing. No, we don't like. So 4 over 25, we could factor it into 2/5 times 2/5. That's what that did. All I did is I said, oh, how do I get 4? Well, it's 2 times 2. How do I get 25? Well, it's 5 times 5. Yep, Kinsey.
Like if you just like did it just like one part and then did the other part and like multiplied it together, would you get the same answer? Like if you like did 2 cubed and then 5 cubed and then like flipped the part.
At some point, you're not going to be able to combine them together, though.
Okay.
Or you're going to have to use your calculator, which means you're not using the properties to do it.
Okay.
So that's what's going on. Yeah. Now, I think it's interesting because most of the time in our minds, we think that stuff with letters is harder. But was Part A harder than Part B? I mean, we're not even done with Part B yet. Part A is not harder than Part B because on Part B, we have multiple ways to represent those numbers, which creates sort of a confusion with what's going on. It makes it more difficult. Let me finish the problem the way I started it, and then I'll finish it from the other perspective so that you can see another option. If we take a look over here at this version right here, we've got the 2/5 in both places, right? So I've actually got 2/5 to the third, and then I've got 2/5 to the negative 12th. Because one of our properties, this property number 3, says that if I have a power to a power, I can multiply the powers. Now I actually have exactly the same base. Each one has a power. What can I do with those powers? I can add them. So then that's 2 over 5 to the negative 9th. Now, go back up to the directions. How are my exponents supposed to be? They're supposed to be positive, and this one's negative. So we can do the reciprocal. You got it. So I can leave this, or I can rewrite this last time. This is the answer now. Rewritten as 5/2 to the 9th. I leave it in exponential form. You do not have to multiply 5 times itself 9 times or anything like that. Yes, Gina?
Unless it says leave it in positive exponents, you can just leave it 2 over 5 to the negative 9.
You could. The directions in your book, I believe, say leave it in positive exponents. That's pretty typical. So yes, if it didn't have that though, you could have left it the other way.
Well,
That's
like
true.
on like a test, most likely it'll say that.
I would probably say with positive exponents, yeah. All right, let me show you the other option. I'm sorry, did you have a question, Ashley? Anna?
On the answer.
Yeah.
Do you have to have the parentheses?
If you don't have the parentheses, you would need to write this as 5 to the 9th over 2 to the 9th,
Okay.
which would be fine too. Yes, Ashley?
And I still don't understand, I get the reciprocal thing, but
Yep.
I still don't get how the exponent becomes positive when you do the reciprocal. I still don't get like why it's positive.
All right, so trying to think of the best way to explain for you. That's why I'm sitting here. So your question is, why in the world does x to the negative 1 simply become 1 over x to the 1, right? Why is that? That negative 1 power is a notation, all right? It's a notation kind of like the multiplication symbol is. So why, when I have a multiplication symbol, do I do this process? Well, I do it because we've defined that multiplication symbol means this is the process we do. That negative exponent is very much the same way. A negative exponent means reciprocal. So when I do the reciprocal, the exponent is no longer negative because it's a operation, right? It's kind of like square roots. Why does a square root take the number 4 and the root goes away when it becomes a 2? Because I did the operation of square rooting. That's the idea. I think that's probably my best way to is it okay? Okay. Let me show you one more option over here to think about. Over here on this one, if you had separated it like this, you could write this then as 2 fifths to the third. You could write 2 fifths to the negative 6th, and another 2 fifths to the negative 6. You can distribute that negative 6 through. And then you can add up all 3 exponents, just like we added the exponents 3 and negative 12 over here together. This 3 and this negative 12 became negative 9. You could add the 3, the negative 6, and the negative 6 to become negative 9. It's just thinking about it from a different point of view. And I'm not asking you to sort of like write down every point of view possible. I just want you to realize that there's more than one way to think through this. So if you were working with somebody else and they said, hey, but this is what I did, that's probably okay. It's just a different way of thinking about it. Okay? And of course, it would simplify then to 5 over 2 to the 9th, or 5 to the 9th over 2 to the 9th. Any questions on that one? Okay. Now here's where we see these used. This is one of the places anyway, is just to be able to solve for certain exponents. Okay? What we're going to be doing here is we're going to be using the properties of exponents as we do this simplification. So A is a really good one for us to think about because the left-hand side looks a lot like the things we were just doing. How do I simplify 2 to the n times 2 to the 7th? What would I do to those exponents? Add them, right? I hear a few of you saying add them. So I could write this as 2 to the n plus 7 on the left. Okay? That's the very first property of exponents that we had. Multiplying the exponents with the same base, so we can add the exponents. Here's the other thing, and this will be true for every single one that we're doing. And we're doing this because this is the elementary level of being able to work with these. These will not always have the property I'm showing you, but you don't get to them having a different property until we get way late in middle school, early high school. So what we're going to do, what we're going to see happen is I am going to be able to take the other side of this equation and write it as the same base, in this case base 2, with some exponent. Do you know what exponent you can apply to the number 2? That is, what number would I have to put here to get back 64? 8. Did you check? Okay. Are you sure? I think that's too big. Lydia's trying. Is it 6? I think it's 6 as well. 2 to the 6th? Okay. And this is a very good exercise for you to be able to check yourself with your calculator, right? If you aren't sure how to use the exponents in your calculator version, like how to get an exponent, let me know and I'll show you how to do that. This is one of those things that calculators vary on, actually, how to get your exponent. But this is 2 to the 6th. Now here's the reason we want this. If the bases are the same, the only way this is equal is the exponents are also the same. That is, this reduces to being equal to that n plus 7, that exponent, has to equal 6, the other exponent. If the bases are equal, the exponents must be equal for the values to be equal. Okay? So once you can get the bases the same, you can ignore them. They don't affect the problem anymore. They don't cancel out. That's not what's happening. You just get to ignore them because they don't effectively do anything any longer. Okay? What's n going to equal here? N's -1. Do you have a question, Jana?
Are the twos always going to be the same, or the bases always going to be
In the problems you're working, you will always be able to get both bases the same.
okay, but let's say
In the reality, when you get to like Algebra 1, Algebra 2, junior high, early high school, that's not always true.
What would you do if it was like 2 to the n plus 4 to the 7th or whatever?
You're going to see that happen on the next one,
Ah,
similar to what
okay.
you're looking at anyway. All right, look at the next one. The left-hand side already says 3 to the n, so it is simplified. Agreed? The right-hand side, however, does not look like 2 to a power. In fact, it looks like a fraction. So what are we going to do with this? Okay, so hang on one thing at a time. I hear reciprocal, and I hear, what did you say, Lydia? Negative exponents. Negative exponent means reciprocal, right, Ashley? That was your question earlier, yeah? All right, so I could take that 1 over 81, and I could write it as 81 to the -1 power. That's where I'll start anyway. So now at least I don't have a fraction anymore. Agreed? Okay. Now, what I still need to do, though, is this 81 has to be written somehow as a 3. It's not that bad, Beth. I promise. What in the world? Okay, so the negative exponent aside, take 3 and raise it to a power in your calculator. What power does it need to have? It needs to have a 4th. You're right. It's a power of 4. In your calculator, try it. 3, raise it to the 4th power. Does it equal 81? Yes, it does. So the 4 is what we're looking for. Now I can use properties of exponents on the right-hand side to write that as 3 to the -4th. It's exciting. Okay? Now, this is not quite the same as when I got to that point here. What's different? Yeah. The first problem, part A, had an equal sign, and the second problem on part B has a less than or equal to. The only effect that has on your answer is that your answer is going to have a less than or equal to. So when you're comparing those exponents, you just compare those exponents with the sign, that is the less than or equal to sign, that you're already working with. So I have the exponent on the first side, the left-hand side, the same sign, less than or equal to in the middle, and then I have the exponent from the right-hand side. And because n is alone already, I don't have to simplify things any further. So that means any value that I put in smaller than -4 will make the left-hand side less than 1 over 81. That's what that means. And while we're working right now in fractions, it's any value n that's less than 4. So maybe less than -4, excuse me. So maybe I use -4.5, a decimal. That's okay. Maybe I go with a whole number and -6. That's okay. Any number that's less than -4 will work. Any questions on that one? Shayna, does that help you a little bit with what question you had?
Yeah, well, I was just confused because if, like, the 2's are different up there and it's, like, 4 to the 7th or whatever.
Sure.
How would you make it 2 and then what would you add the top to, like, what you... I don't think I'm explaining it very well. But...
Okay, let's say that it looked like that.
Yeah, but you
Is that your
want to
question?
get to 2.
Sure.
So would you just add the 2 to the 7?
No, well, you're on the right track, but not with addition. You would rewrite the 4 how?
You would do 2 and then square.
You'd rewrite the 4 as 2 squared. And then you wouldn't add the exponents. What would you do? You multiply them.
So
That's property number 3.
14.
Right.
Oh, okay.
And there will always be the ability in the ones we're doing to do something to get the bases the same.
Okay.
Okay? And sometimes you may have to manipulate both sides in order for that to happen. That's a possibility too. All right, let's do an approximation problem. Number 8, approximate the following product. 20 and 1/3 divided by 9 and 7/8. What is that approximately? 2. Why? This is almost 20, and 9 and 7/8 is almost 10, right? This is an approximation problem. So if that's the case, well, I'll use approximately again. Then the answer approximately is 2. Okay. This is the kind of math you do at the grocery store, right? Yes, you make sure that you get up to the register and actually have around the right amount of money. That's a good thing to do. Yeah. Approximation. All right, here's a fun one. Jasmine is reading a book. She's finished 3/4 of the book and has 82 pages left to read. How many pages has she read? A lot. She's read a lot. There's a couple ways to do this particular problem as well. Think about it for a second. Hannah, do you have a suggestion? Okay.
Wait, are we supposed to study approximately? Oh, no.
Nope, this one's going to find it exactly, yeah. That's a good question since it follows the approximation question. It wouldn't be 3/4 of 82. Because 82 is not the 3/4 she's read.
Right.
And it's not the whole book either.
Could you just multiply by 3?
Okay, all right, so that's a good way to do it. So what you're saying is, I'm going to write it down because I don't think that you guys have thought through it quite as clearly as this, but this is what you're equivalently saying. You're saying that she has 1/4 of the book left, correct? And 1/4 of the book is actually 82 pages, correct? Okay, so what I could do is then I could say, well then 3/4 of the book that she's read would be the 82 pages times 3. Does that make sense? That's a great way to do the problem. So tell me then, what is 82 times 3? Grab a calculator if you want. But what is it?
246.
It is 246. Very good. She has read 246 pages. What if it asks you, how long is the book? You add 82 to the 246. Be sure that when you're working problems like this that you're really clear on what they're asking for. Because it's really easy to get caught up in how to do the work for it that you don't actually answer the question they ask. So just be real clear that your answer is to the question that they asked. Okay, we have one more in this section. Al gives half his marbles to Bev. Bev gives half of these marbles to Carl. Carl gives half of these marbles to Danny. If Danny was given 4 marbles, how many did Al originally have? Okay, so how are you guys processing this? You're working it backwards. That's the word I want to use. You're thinking about it in a backwards way, right? So we start out with Al, and then we went to Bev, then we went to Carl, and then we ended on Danny. Danny, in the end, had 4. He got those 4 from Carl. So how many did Carl originally have? 8. But then he gave away 4, right? Just keep that in mind. So Carl doesn't really have 8 any longer, does he? So if the question actually asked you, how many does Carl now have? The answer would not be 8, correct? It'd be 4. Now, it doesn't ask you that, but I'm wanting to make sure that you understand that if the question had been asked slightly differently, your answer to the process that you're working through would also be different. How many does Bev originally have? 16. So how many did Al originally have? 32. How many does Al have now? 16. Good. All right, so Al had 32 to start. Any questions on that? Okay.